in the past, we took double integrals of surfaces over these rectangular regions, and what that gave us was the volume of that surface, like underneath the surface within that region, right? So if you had this rectangular region, and we're gonna say like it's within like the or like it's bounded by x, the y-axis and the x-axis, as well as this line y equals a going like so, and then x equals b going like so, right? This line. Then the intuition was kind of like, okay, well, to find the area, you're essentially what you're gonna do is for some value of y, like let's say here, right? We're gonna go along this line, and we're going to go along this line starting from x equals 0 all the way to x equals b for some constant y. We are going to take all the small little dx's, right? There's going to be this little dx right here, and you can extend that, right? You can extend that to the surface. And at the surface, this point right here will be f of x, y, right? That's like the height, right? Like the three functions, right? You give it a chord, like a pair, an ordered pair, and it outputs a height. Now, you could go ahead and you would get this very small area dA, right? dx times a height, that gives you some area dA, and you can integrate all those areas to get sort of the cross-sectional area at that y value. So in other words, the cross-sectional area at some value of y is going to equal the integral f of x, y, in this case dx, right? Because we're adding up all the dx's, and then we get the cross-sectional areas. Well, how do you get the volume? Well, what you can do is you can take, right, all of the and by the way, the bound, I totally forgot, it's from 0 to b, right? We're going starting at x equals 0 all the way to x equals b. And well, how do you get how do you get like the volume? Well, what you do is you just take you just get all the cross-sectional areas, right? There's going to be a cross-sectional area at this, this y value. There's going to be a cross-sectional area at this y value. And what you notice is, well, this cross-sectional area is going to be some function of y, because when I'm done taking this integral, y is treated like a constant, right? So it's going to be, the cross-sectional area ends up being some function of y, and we're going to integrate that. We're going to, you get a little small section dv, right? A small area and volume by multiplying dy by that cross-sectional area. You get this kind of slice, like a loaf of bread, but a really thin, or slice of bread, a really thin slice of bread. You add it all up and you get the total volume. So that's really just integrating the integral, right? I'm taking this integral for all dy's from 0 to a. This is what we kind of came up with in sort of the last video, albeit not as concise, because I think when I was making that video, I was like really tired or something, and so I didn't explain it as well as I did. But that's the intuition. Now, how do we do this for general regions? Well, I'm gonna use a different marker. What does a general region mean, right? A general region would be something like, like this, right? Rather than a rectangle, we're now gonna get the area under some sort of other region. This could be a curve, right? Well, really, this line that I drew here, if this is, the point, let's do BA, just to be consistent over here. If this is the point BA, then this line is really just defined as y equals, I think, B over A, right? No, A over B times x, right? But this could be any curve. This could be like x squared, this could be x cubed. How would I go about doing this? Well, it's the same intuition of taking slices, but now your bounds are kind of changing. Here's what I mean. Think about this, right? You're gonna do, we talked about the theorem. It's by some fancy guy. You can flip this, right? This is also equivalent to integral 0 to b, 0 to a, f of x, y, dy, dx. You can flip this, right? Because you can do the same process, just instead of, starting off with, you can start with cross-sectional areas along the y-axis and then sum those all up along the x-axis. So now, let's say we were to do this the other way, and we were going to kind of say, okay, well, I'm going to start here, right? Well, what is, when we're doing it like, when we're taking this length, right? In this case, so because we're doing it along the y-axis first, this is what we're essentially doing. We're gonna, oh my god, this is kind of ruining the drawing. Maybe I should have started it like this. But essentially what we're doing is we're gonna say, hey, along the y-axis, we're gonna kind of extend that line, and then we're gonna take all the little dy's, right? And then we're gonna get the cross-sectional area like so, right? That's the inner integral. Well, here, there's, the length of that line that we're integrating along is 0, right? It's the same as integrating from 0 to bound 0. Here, we're integrating from like 0 to maybe like, I don't know, 5. Here, we're integrating from like 0 to 10. So each time we integrate the inner integral, the bound is changing. And really, what happens is the bound is changing, right? But, remember, in the last case, this y was a constant, right? In the last case, it was maybe, we were integrating to y equals a. But now, this is actually a function of x. This changes as x changes. This is going to be a over b times x, right? So, this is a over b, x. So we're going to do f of xy times dx, right? So as we go along the x-axis, as we're integrating, right, the bound is kind of changing, which is kind of weird to think about. Oh, I'm so sorry. This should be dy. This should be dy. So, and then we're still going to do the same thing where, this boundary is kind of fixed. We're going to take the double integral, right? The outer integral is going to be from 0 to a, or b, 0 to b. Okay, yeah, there we go. 0 to b dx. So take a look. This integral is still a function of x, right? You put in some x value, right? Whether you're doing this line when you're taking this line integral from 0, from x equals 0 or x equals 5, x equals 10, whatever, right? You input that in, and we're taking this integral with respect to y. And then at the end, you take the outer integral with respect to x. We're going to talk about how to solve this. Now, this is what we would call, in this scenario, this is what we would call, I think, I believe this is type 1. So what does type 1 mean? Well, a type 1 double integral just means that, hey, if I were to get my region, it looks kind of like this. This is my region of integration. Well, really, I'm doing, I'm kind of, I'm integrating with respect to, well, first, I should say the inner integral is being integrated with respect to y. I know this because I can kind of draw lines and kind of be like, okay, my top curve here is changing, so I'm going from kind of top to bottom, right? So I'm integrating from top to bottom. Now this is what we call type 1. And then the outer integral has the bounds where the left and right bounds are fixed. Does that make sense? So I know it's type 1, and I know to integrate with respect to y first, because top to bottom, which is like the y-axis, right? That is changing. That's the one changing. So I want to do that first, and then I integrate the outer with left and right, which is fixed, right? So, what do you call it? Wow, that's left. Oh, yeah. What I'm trying to say is x direction is left and right. So that's how I can kind of remember. Type 2 would kind of be something more like this. So let me erase this because we don't really need this now. But for type 2, I get something more like this. So, now I don't want to integrate. Oh, this could also be considered. Okay, let's make it more curvy so it's like more clear this is type 2. So maybe this is like a sine curve. I don't know. Well, now I don't really want to go top to bottom, right? That would be a pain in the butt. Think about it. Because in this case, in type 1, it's like the top curve is very clearly defined by one function. Here, it's like, okay, well, if you go top to bottom, it's just a straight line. But then when you go top to bottom here, then it's a different function, right? So I don't want to do it like that. It's kind of like in Calc 2 when you did the integrating to find volume or whatever. Like the whole... Oh, I don't even remember, to be honest. But hopefully this is kind of familiar to Calc 2 when we were doing the whole integrating to find volumes based off cross-sectional areas, if you remember that. Now I would just kind of do it left to right, or right to left, right? Because in this case, I'm doing the left function minus the right function. That's another thing, right? Really, this 0 is my bottom function. This is when y is equal to 0. If I had something like y equals, I don't know, y equals 1 over a times x, right? Maybe then I'm doing the top minus the bottom, right? I'm taking the top length and subtracting by the bottom length to get what's in between. So this would be like 1 over a times x, right? So yeah, you're doing top minus bottom function. Here you're doing right minus left. So because I'm integrating along the x-axis first, I'm doing, so this is kind of crazy, right? You have to get a function, g, in terms of y, right? g1 of y, g2 of y, right? You're taking kind of the inverse function. And it kind of makes sense, because if you were to reflect this along y equals x, which is what an inverse function is, you would get top minus bottom. You know what I mean? Like if you were to reflect this over, you would get, oh, this is probably not accurate. Would it be like this? Yeah, I think so. You would get this curve, right? This is what your curve would look like. So it's really top minus bottom. So you're taking the inverse really, but it's g1 of y, right minus left, f of x, y, dy, and then integral, and then 0. So you're doing now your top bound to your bottom bound. So like, you know, b to 0, right? Or whatever your bottom bound is. Once again, you know, you could have more of something like this, right? So you're doing left bound minus bottom bound. Okay. Or sorry, yeah, in this case, for the outer, it's going to be right bound minus left bound. In this case, it's top bound minus bottom bound for the integral. Now, well, hey, what if you get a region that looks like this? Okay, well, this is probably too complicated. Okay, what if you get a region like this? What if this is your region? Well, even this is not a good example. Okay, let's see, what's a good example? Let's say you have a region R that maybe kind of looks like this. Is that a good example? Yeah, we'll just roll with it. What you can do, if this is our region R, you can use this property of integrals. The double integral of this, across this region R, f of x, y, dA, is equal to, right, and remember this is a notation we talked about last time. You can actually split this up. You can make your own bounds, right? If you know each of these can be considered like functions, right, because they all pass the vertical line test, then you can split this up into like R1 and then R2, R3, which I don't think you really have to do. Like you won't come across problems where you really have to do that. But just so you know, you can do R1 f of x, y, dA. It's a property, right? R2 f of x, y, dA, plus and so on. So let's go over some examples and talk about how you can actually evaluate these, because they're a little bit tricky to evaluate sometimes. Okay, let's do this example. Let's say we have this function, or we're taking the double integral, I should say, of a function. So let's say we are doing double integral of r. Let's do, or Yeah, I'll just do y. Or r. Y squared e to the xy dA. And then where r is bounded by y equals x, y equals x, y equals 4, and x equals 0. So first step, what I would do is draw your region just so you understand what kind of thing we're working with, right? Like what kind of region we're working in. Is it type 1? Is it type 2? So if I were to draw this out, I know it's going to be bounded by y equals 4 and then y equals x. So it's this region right here. I'm going to use a different marker. God, these markers are crud. Okay, maybe I'm complaining because they do have a decent amount of ink. Whatever. We know this is when y is equal to 4 and y is equal to x, so this is at the point 4, 4. And then hopefully you know this is also bounded by like x equals 0, which is just the y-axis. So now what you can notice is that this is actually a type 1 and a type 2. I think this is what, type 3 maybe? Let me just check my notes. This is like both. Like you can do top, bottom, or you can do left and right. There will be no kind of conflicts with, you know, oh, it's going to be a different curve or whatever, like we saw in the last example. So this is type 1 and type 2. Now, you can choose, right? Do I want to do dy dx with my integration, or do I want to do I want to do dy dx for my integration, or do I want to do dx dy? You got to choose what makes it easier, right? Let's think about this. If I were to do first dy, kind of a pain in the butt because we're gonna have to do, like, we have y squared, right? Because we're integrating with respect to y where x is treated as a constant. Well, you're gonna have to do like this, like y squared, you know, like you're gonna have to do this maybe, what do you call it, that integration by parts. I don't really want to do that. Maybe I want to integrate with x first, right? So then I can kind of, you know, I can already kind of predict that, hey, this is x times y. I know I'm gonna have to get a 1 over y soon. Right, that's kind of my reverse chain rule. Let's start with x first. So let's do this. So I'm going to take double integral. Oh, did this really dry out while I was talking? Oh my god, this is kind of annoying. Okay, we're going to use green. How about green? I don't use green too much. It's a little faint, but we're going to roll with it. So integral, double integral. We're going to do, so we're doing it with respect to x first. So I gotta think, okay, I'm integrating along the x direction. So if I'm integrating along the x direction, I need to go right minus left. So my right function is x equals y, right? Because this bound needs to be an x value. So I know my x value is gonna be x equals y. It can't be y value, right? That's why I'm not putting x. Even though it says y equals x, I'm putting y because I know it needs to be an x value, not a y value. But I know it's kind of confusing because it's like, wait, you're literally putting y. What do you mean not y value? But remember, this is a function. This is really a function, right? H of y is equal to y, right? This is a function. So I'm saying h of y, which spits out x, right? It spits out an x value. Well, it's just equal to y. So that's my function of y, right? H of y is just equal to y. In the same way, it's like f of x equals x. So we're doing from y, and then that's my right curve. My left curve is just x equals 0. And then for my kind of top minus bottom, my top bound is 4, and then my bottom bound is 0. So I'm going from 4 to 0. Right? Yeah. I'm going, yeah. Okay, that makes sense. Because you're doing this cross-sectional area, this cross-sectional, you're going all the way down to 0. So let's just solve this integral now. Y squared e to the x y dx dy. I want to integrate with respect to x first because I'm dealing with x bounds. So this is not too bad. I can pull the y squared out, in fact. I can pull the y squared out. E to the xy dx dy. So for this interintegral, I know I have to do reverse chain rule. if I were to take the derivative of just e to the xy, then I would get, with respect to x, so taking the partial derivative basically, if I were to take the partial derivative with respect to x, I would get y times e to the xy, where y is treated like a constant. So I know I'm going to need to put a 1 over y in front, right? So when I take, the derivative of this, I would get, let's do it like this, 0 to y, right? Our bounds need to match. So I would get 1 over y times, when I take the derivative, I would get e to the xy, so I would get the y in front. Y times 1 over y equals 1. I'm left with just e to the xy, which is my antiderivative. So it works out. Now, all I gotta do is I gotta substitute in my bounds, right? So really, I can pull this 1 over y to the front. So I get y times, now I need to substitute in all of my x's need to become y's, right? I integrated with respect to x, and my bound is y. So I need to make this now equal to y. So I would get e times y minus e to the 0 times y. And then you can probably see you would get you would get y times e to the y squared minus y, right? When I distribute the y over, y times 1, right? Negative 1. And now I can just, this is actually not too bad to integrate. I can separate the integrals, right? So I can say, this will just equal minus 0 to 4 y dy. And you can do u sub here. I can say, hey, u is equal, and then this is also integral, 0 to 4, whoopsies, y e to the y squared dy. So I can say, hey, u is equal to y squared, and then du is going to equal 2y dy, or 1/2 du is equal to y dy. So now I would have a 1/2 out of the integral, and I can substitute in and be like, okay, well, this is really going, u of 4 is equal to 16, and then u of 0 is equal to 0. I'm just doing y squared, so 4 squared is equal to 16. And then I'm really doing 1/2, and then this is really integral e to the u du. And the answer to that, the antiderivative to that, is e to the u, right? I just dropped my eraser, so that's bad. But I would get e to the u, and then my bounds from 16 to 0. And then for here, I'm doing really 1/2 y squared. This is just reverse power rule. And then, yeah, this is not too bad. I get 1/2 e to the 16 minus 1/2 times e to the 0, which is just 1, so minus 1/2, minus 1/2 times 4 squared, so that's 8. And then, I don't have to worry about the 0 because I'm doing 1/2, 0 squared. So I get this answer. I'm going to see if it's correct, and if I messed up along the way, it'll be a teaching moment. I think that's right. I'm pretty sure it's right, because this is really 16 over 2, and the answer key says e to the 16 minus 17. Yeah, that looks about right. Cool. All right, let's do another example. So, for the other example, let's see what's a good kind of... I'll do 2 more. How about that? Okay. So, this is kind of a crazy one. Let's find the volume. So we want to find the volume under the surface. So fine, let me turn on the lights real quick. Let me just see, just out of curiosity, how long this video has been going on for. 23 minutes. Okay, we're just gonna spend maybe another 10 minutes on these examples, hopefully. So find volume under z equals 2x plus y squared above region. So we're going to do above the region bounded by x equals y squared and x equals y cubed. So first, let's just draw our region. So if we had this region, and I think in the first, well, no, it wouldn't matter. You'll see in a second. So x equals y cubed. Well, I know y equals x cubed will look something like this. And then I know y equals x squared will look something like this. And they'll intersect right here. And they'll intersect at 1, 1. Now, how do I know which is on top and which is on bottom? Well, you know, if I think about it, I'm taking, if this is y, so this is y equals, you know, these are functions of y. Y equals x something, y equals x something. Well, if I take a number less than 1 and I cube it, it'll be less than if I square it. Does that make sense? If I take 0.4 squared, I get 0.16. But if I take 0.4 cubed, I think I would get 0.064. I might be wrong on that. But, you know, I'm multiplying more decimals. I'll get a smaller number. So I know the function on top is x equals y squared. Function on top is y equals x cubed. So these are the inverse functions of it. So remember, it's the same as reflecting it along y equals x. So if I were to reflect this over, I would get something that looks, if you visualize it, I would get something that looks like, let me draw it out better. I would get something that looks like this, right? Reflected over y equals x. And since the top was y equals x squared, I know the right curve, like the curve to the right, is going to be x equals y squared. And then the curve to the left, which was previously on the bottom, is x equals y cubed. So this is good to know because this is a type 2 region, right? Like you're going to be integrating with respect to x first because that's what's changing, and then the fixed bounds are in the y direction. So that's good. And then remember, it's 1, 1. All right. And I know that this is also, you know, if I continue y equals x squared, I would get something like this. And if I were to continue x equals y cubed, I would get something like this. So I know they don't overlap except for this region. So let's take this. So I'm doing it with respect to x first. So if I were to take this double integral, I'm doing 2x plus y squared dx dy. The right curve is y squared and the bottom curve is y cubed. And then the bound, right, from top to bottom is from 1 to 0. Now, this is pretty simple to evaluate. You know, if you treat this like a constant, or if you treat y, okay, well, I should do this first. For the first 2x term, hopefully that's pretty simple. That's just x squared from reverse power rule. And this is really like a constant, right? This would be the same as integrating 4 dx. So this would be the same as doing y squared times x, right? Because it's a constant. If this was integrating 4 dx, you would get 4x. If I'm integrating y squared dx, I get y squared x. So this is from y squared to y cubed. And I'm integrating with respect to y. So from 0 to 1, what I'm doing is I'm going to be saying, okay, well, I'm just substituting in my y squareds. So I would do for x, right? So y squared squared, that's y to the 4th, plus y squared times y squared is y squared times y squared is also y to the 4th. Minus, right, because FTC, fundamental theorem of calculus, I put the y cubed here, I get y to the 6th. And if I do y squared times y cubed, I get y to the 5th. Yeah, that makes sense. All right. And times dy. So this is really the same thing as 2 y to the 4th. And this is just good old power rule derivative, or like a polynomial derivative, or integral, there we go. So I would get 2/5, right? 2/5 y to the 5th minus 1/7 y to the 7th minus 1/6 y to the 6th. And then I'm doing from 1 to 0. When I plug in my zeros, the whole thing returns 0 anyway, so I don't have to worry about that. I just plug in the ones, and I get whatever this simplifies. So 2/5 minus 1/7 minus 1/6. Which I always thought is like the coolest thing ever. Like when you're, yeah, that's the correct answer. 19 over 2/1. I always think this is the coolest thing ever. When you're taking this volume of like a really complex shape, you'd expect it to be like something like, I don't know, 17.1514 721, something, I don't know, crazy irrational or something, just a complex number. No, it's just a simple fraction, right? I just think that's cool. I don't know. All right, last thing, we're just going to talk about reversing bounds if we need to. So let's say we had this function. Let's say we had this function. Let me just go to the notes just so I can see. Oh, yeah. Okay, let's say we had this function, or this double integral. 0 to 1, x to 1, e to the x over y, dy dx. If you were to start taking this integral, it would be kind of a pain in the butt, because you would have, whoa, with respect to y first, I have this like e to the x over y. It's like this exponentiated rational function. That's really weird, and I don't know how to take the integral of that. So we need to reverse the bounds. We can do dx first. So in order to do this, we first have to look at, well, what region are we integrating over, right? I'm going to use green for this. So in this scenario, I would say, okay, well, so I'm integrating with y first. So this tells me these inner bounds, right, are going to be, right, if I'm integrating with y first, I'm going top to bottom. So this will be my top bound, y equals 1. And then this will be my bottom bound, y equals x. And then if I'm, and we can continue these because we don't really know what the left bound is, but dx is the outer integral, so I know my left bound is 1, and I know my right bound is 1 and my left bound is 0. So I am integrating to the y-axis. Now that I know that, it's actually pretty easy, because then I can make this a function of, or I can reverse the bound, because I can say, okay, well, this is f of x equals x. So if I were to swap my y's, my x's and y's, right, that's how you get an inverse function. Well, I just get f of y equals y. So this will be my right bound. And then my left bound will be x equals 0. And then from top to bottom, it's pretty simple. It's just 1 to 0. So if I were to evaluate this integral now, my right bound is going to, or my right kind of bounds, like my inner bounds are going to be f of y equals y to 0. And then we're going from top to bottom, 1 to 0. Cool. So we're going to do e to the x over y dx dy now. And this is pretty easy to evaluate, because you're kind of saying, okay, well, from 0 to 1, the integral of this will end up being y times e to the x over y. Because this is just reverse chain rule, you would see like, hey, if I were to take the derivative of just e to the x over y, I would get 1 over y times e to the x over y. So I need to multiply by y so that I get rid of that y term. It's just e to the x over y. And then this bounds are from 0 to y. I'm integrating with respect to y. Whoops. Okay. From 0 to 1. So y times e to the, x over y, and y over y is e to the 1, and then minus, because I'm really doing I have to, do y times e to the x over 0, well, that's just 1. Or 0 over y, that's just 1. So I get y, this whole thing turns into 1. dy. So if I want to be fancy, I can factor out the e minus 1 term and then pull it out of the integral. I'm gonna make a dirty joke there. So integral 0 to 1 y dy. This is e to the 1, e minus 1, sorry, times 1/2. Well, it's y squared, which is just 1 squared minus 0 squared, and I get 1/2 e minus 1. So yeah, this is a pretty